Okay, I'm going to try it out sometime this weekend. Okay. Current carrying conductor in a magnetic field. Okay. Okay, you got that? Yeah. Now, a couple of formulas here to look at. So, here's another example of the left-hand rule. If a current is moving this direction and the field is moving this direction, then there's a force upwards here. This makes us realize if a charge moves in a magnetic field, then it'll experience a force. What about a current? Because a current is just charge per time. The answer is yes, of course. And let's figure out the formula. We can just modify this formula, F equals QVB. So this time, instead of a single charge moving in the magnetic field, we'll have a current moving in the magnetic field. Do you see the difference? Yeah. Last class we did just a single Q, like an electron moving in the field. But now we're looking at a full current, like if I had a wire, you know. So anyways, let's have a look at what formula we can make here. Let's say that it had the wire, yeah, has a length L as well. Okay. Yeah, and you're also right, Zach, Q equals IT. You confused me now. I equals Q over T. Yeah, so Q equals IT. We did that formula in electricity. So that's equal to ITVB. But this one here is interesting. T times V. If we think about our triangle. Yeah, distance. Let me draw it again. Distance, which is length, speed, time. So this here would be a length. So that's an L. So you can quite nicely write the formula as BIL, B-I-L. That the force on it will equal the magnetic flux density times the current times the length. That's the formula. So this is a little simple little proof. Now, what's kind of interesting, I think it's this formula. No, it's not this formula, it's the next one. I'll tell you when I get onto it. Okay. I think it's good if you can write this proof down. It's a short little proof. Zach, how can you drink those drinks? They're disgusting. Have you no taste buds? What flavour is that one? What flavour is that one?
Doesn't actually say.
Cat pea flavour, that's what it is.
Citrus flavour.
Citrus flavour, okay.
It's more of the caffeine that I'm addicted to.
Don't like cups of coffee?
Nah, I don't drink coffee.
No. Tea?
No.
Just cold drinks? No. I don't know. I don't like those drinks. Red Bull as well. Don't like it. You know what's funny? Actually, the European headquarters for that company, Monster, believe it or not, that's opening up in my hometown.
Really?
Yeah, where they're going to, the new location for where they produce and bottle all these drinks in Europe will be in my hometown, like 5 minutes out away from my home.
I thought they made them in Netherlands.
Yeah, but I think they're moving their headquarters because there used to be a Coca-Cola factory in my town and that closed, and then these people bought the factory. It should be opening this year. So I don't know. Maybe I'll be able to get you free ones. All right, continue. So we have F equals BIL. Yeah. Now in this formula, the current is perpendicular to the field. If it was not perpendicular, that is, if it was at an angle theta, then let's see what the formula is. Okay, so this is going to be a bit hard to draw. I'll do my best. Oh, I don't even know if I can. I'll try. North, south, field, and instead of being perpendicular like this, we'll put it at an angle. Like this instead, okay? We call this angle theta. So actually, this component here, we'll call it IX. And then this component here, we call it IY. And we don't care about which one. We don't care about the IY. Because what I didn't tell you, well, you can probably see this. In the left-hand rule, it only works if the things are all perpendicular. Right? It doesn't work if you put at an angle. It's supposed to be perpendicular. Okay? So that means the IY has no effect. It's only the IX we care about. And the IX, yeah, it'd be I cos theta. Now, I think that's if you measure the theta here. If you measure the theta here, it would be sine. But I think they usually measure the theta here. Let me check actually before. Oh no, rats. Sorry. It's the other way. Yeah, so they measure the theta here with respect to the field. Okay. So it's sine then. So you get F equals BIL sine theta. And I think it's worth writing that down, but also writing down here that the theta is, do you know what WRT stands for?
With regard to?
Yeah, with respect to the field. Yeah. Is it okay, Gina? Yes, no?
So, wouldn't the current need a medium to pass through?
Yeah, so this would be like a copper wire.
So how, wouldn't that just be stationary? Why would you want the copper wire to move?
Oh, you'll see. There's a good reason for it. You'll see. Good reason. Continue? No.
I'm saying like a ghost rifle.
No, it doesn't have to be anything fatal like that. Okay. You got that? No? Sorry, it's a little bit messy. This was kind of the second half here. Oh, sorry. So actually, yeah, this is, yeah.
Do we do?
No, don't write IX because they don't do that in the exam or the formula book. So I was just doing this as a proof to give me this formula. I mean, you can write it down if you want, but I just care about this. Yeah?
Do we do motors today?
I
And
think
generators?
I think that will be in this slide, yeah. Maybe not the generators. I'm not sure. I think it's too much. We might, we'll see. Okay, can I continue? Yeah. So, if a force acts on a current in a magnetic field, then could we use this force to do work? Yes, we can. And this is exactly how we do it. This is called a DC motor. Let's have a look at how it works. So, the current moves along here, enters via the brush on the left into this, what's called armature, and then exits here. And it's important that there's no connection here, because we want to force the current here. We don't want the current just to do this. Okay, so there is a little gap here. Now, let's think about what's happening here. If I use my left hand, which way is the field going?
This way.
To the left. And which way is the current going? No, sorry, north to south.
Into
Yeah, this is. And which way is the current going? Into it. Well, that doesn't seem right.
like this, yeah, upwards.
Hang on, I need to stand up and do this.
North to south. Like that.
Oh yeah, here we go, yeah. This is it. Oh, who the heck is calling me? Who is this person? I don't talk to you. Reject. Okay. Right. So, what was I saying? Oh yeah, so the field is that way, the current is that way, so the force is up, as shown on the diagram. Now over here, the only difference is the current is now towards you, so the field is down. Yeah. So what happens if there's a force up and a force down here? It rotates. So we've just made a DC motor, as electric motor, you know. This has been around for a long time. I'd like to think this has been around since like, I don't know, 1880, 1885, you know. The underground in London is electric, but I mean it's been electric since like 1900, you know. So it's reliable technology that's been around a long time. You know, even in electric cars or electric motors of any kind, it still uses this principle. So,
much more efficient and manufacturing tolerances.
yeah, the only thing that's different is the material has improved. It probably doesn't get as hot. Anyways, just some vocabulary here. So these guys here,
Commutator.
yeah, commutator, or commute, I call them commuter, but I shouldn't really, commutator brushes or rings, and here usually carbon brush. So I can kind of show you here. What happens is you have a brush and the carbon brush is touching the ring, so it can still turn. You realise if the carbon brush was connected, then you'd have a problem, because when it turns, it wraps around it. So the carbon brush just presses against it as it turns. Yeah. So that's usually, it doesn't look like it in the picture, but that's usually like a carbon brush. And this would be a metal ring that's broken in the middle. And that's it. It's very, very simple, but it just works very, very well. Anything that's rotating works like this. So for example, in the computer, you know, you have the little fan that turns. Yeah, that would be using one of these motors, you know. What else do we have? The Lewis. The Lewis uses this. It's an electric tram, you know. Now, I'm sorry to tell you this, but may need to draw this in the exam.
What?
I'm sorry, but I don't make the exam. There's a possibility they could ask you to draw a DC motor and label the parts. Now, what I would hope is if they did test this, that they would give you the diagram and ask you to label it. But I can't make any promises in life, so you should copy this down.
And then they ask like how it can be made more efficient.
No, they wouldn't ask that.
They don't ask that?
I don't think so. It's not a learning outcome. I don't think so.
I remember that, those sort of questions. Use a horseshoe magnet instead of
Really?
a
Okay.
round magnet instead of a bar magnet. Increase the current.
Okay. Not part of the learning outcome. Yeah, that's fine. Yeah.
When you say label, do you mean like the parts as well?
Yeah, like the words I haven't read there. Well, obviously, you know, south and north, but the commutator and the brush and the armature.
Split train commutator.
Yeah. You have this drawn? Yeah. Is it hard to see, Gina? It's okay. Continue? Yeah? Okay. So, let's calculate a formula, let's find a formula that would let us calculate the torque. You remember torque turning force? Yes. Now, if we have a look at the picture, we have a force this way and a force this way. So what do we call this type of arrangement? Do you remember its name? No. No. A couple. Do you remember this?
Yeah.
Are you sure? So what's the formula for calculating the turning force here? If that's D.
F times perpendicular distance.
Yeah.
Half.
Yeah. This is the formula for a couple. Gina's checking her notes. You're looking for this, yeah? Did you find it? Yeah. Where is it? Yep, that's the one. FD. Okay. So, what is the formula for F? B-I-L-D. However, LD kind of represents something interesting here. What does LD represent? LD. The area. Yeah. But also, what you can do, here I have one wire, but actually what they often do is they maybe have this wrapped around a few times, like a copper wire wrapped around a few times. So, if it's wrapped around n times, then all that happens is this just gets an n. Now the way I like to remember this, somebody pointed out that you can spell IBAN like in the bank. Now what's interesting is this is not in the formula book, but in the exam they kind of expect students to prove this. However, if you know the formula, you don't have to prove it, and if you just write the result down, then you get the marks anyways. So it's good to remember this formula. It's not in the formula book. You know IBAN from the bank, don't you? IBAN number. Yep. Okie dokie. Continue. Dorian? Okay. Yeah. Okay. I don't. Right. Now, recall that flux over some region of space is the number of magnetic field lines. However, imagine now that the field passes through n identical regions we are interested in. Let us find a formula for the total flux. This is kind of an interesting situation. You remember that if you had some area, and let's say you have two field lines passing through it, then here we say the flux is 2 Webers. Okay. Now what's interesting is the area could be any shape, so like you could have an area like this. And now it would be 3 Webers. Okay. But you can also have this. The areas don't need to be connected, so you could have a picture like this. So each one of these would be 2 Webers, wouldn't they? And this could be area, area, area. So the flux for one area in this picture would be 2 Webers. But the total for all the areas in this picture would be 6. Or obviously, more generally, the total flux would be n times the flux for one area. Okay, so if I call this something like total, and this here for one area. And of course this only works if all the areas are the same and the same field passes through the areas. Now, this here actually has a special name. I call it total, but the name that is often given to it is what's called the linkage. So I might have it written down here. Yeah, the total flux is n times the flux for one. Oh yeah, and also, remember you have the formula B equals flux over area. So if you want, you could also write this as the total flux linkage is NBA, like the basketball. Now, just before you write that down, oh yeah, now we have to talk about angles. You want to make note that linkage is another word in this context for total. This is an example just. Okay. Why do you think the word linkage is used? is a little bit like a chain, isn't it? Their areas are linked together. Do you get what I'm saying? Like a chain. Okay. Continue. Yeah? Okay. So, oh sorry, do you need a minute? It's okay? Yeah. Well, the next thing is still continuing from this. So, what do we do if the field makes an angle theta with the normal of the region of the space? Okay, so let me try and draw that. There's the region of the space. Oh, how am I going to draw 3D? Oh, I'll draw it on the side. Okay. There's the area. There's the normal. And let's say there's the field. And now they are at an angle. Guys, if I use this picture here, what is the theta in this picture? Is it 0 or 90 in this picture? And remember, it's like this. No, it's 0. Because a theta of 0 would mean the field is perpendicular to the area, which is like this picture. The field is perpendicular to the area. Yeah? So in this one here, the theta is 0. Here, the theta is not 0. So just like before, if that's theta, oh my goodness, then this is theta, and this is cos, and this is sine. And which one would we care about, the cos or the sine? The cos. So the only difference between this formula when there's an angle is what appears? Cos theta.
Let's say it's the field lines are crossing not at a perpendicular angle. But when you resolve it, you assume that the field lines are the same amount, same number, but it could change.
How so?
Like if you think about it, like the field lines say there's 2 through the area,
yeah.
but then when you resolve it, the one gets left out because of the.
Oh, yeah, well this is the problem with the definition, you see.
Yeah, you can't assume that.
So we're kind of pretending there's such a thing as field lines. There's not really. Did you look up the actual definition of Weber? No. So I invite you to. Okay. Continue. Right, here's a very simple example for you to practice. A copper wire has 2 amps of current. The copper runs through a magnetic field. The copper is 20 centimeters long and the field has a flux density of 3 Tesla. What is the force? So what formula do we need here? Bill. B-I-L. And then the second part, what formula will we need?
Bill cos the sine theta.
Yeah. Yeah, so tell me the 2 answers here. Yeah, it's 2 times 0.2 times 3. So is that 1.2 newtons? And then if you multiply that by sine 80 degrees, we get what? 1 newton?
In radians.
1.18.
Oh, okay, 1.18 newtons. Okay, pretty straightforward, isn't it? Can you just write that little example down? Your calculations, then we'll look at another example.
And for all these formulas, we also assume that all the energy is contained.
Oh, yeah, 100% efficiency. Yeah. Okay. Will I do the next example? Yeah. Continue? Yes? Zach? Yeah. So next example, another easy one. A DC motor turns a wheel, current of 3 amps, flux density of 5 Tesla, a 1000 loop of square 20 centimeters, and it's attached to a wheel. What is the torque? So what formula do we need here? I-band. Yeah, I-band. Alright, so you can give me the torque here. Yeah, you did 3 times 5 times 1000 times 0.2 squared. Yeah. And what did you get?
1.2. It's a square, so it's 20 by 20.
Centimeters.
Yeah, I know.
Okay, so 0.2 squared.
Oh yeah.
Did you put 20 squared?
No.
Okay. Sorry, what's the answer, Dorian?
600.
600 newton meters.
That's a lot.
Yes. I don't know if you could get 1000. Could you?
Could be, but not a lot.
Yeah.
The new Lotus Evija,
Yeah.
the all-electric hypercar, is 2,000 newton meters of torque.
Right, okay.
It has 1 horsepower for every kilogram
Okay.
mass, so it's about a 1-to-1 ratio.
And has 2000 newton meter.
No, it's 2,000 horsepower, 1,000 newton meter.
Are you sure it's 2000 horsepower? That
Yeah,
sounds like
it's 1,700, I can't remember.
this is a sports car, right?
It's a hypercar.
Oh, okay.
It costs more than 2
Okay.
million,
Okay, okay, fine.
£2.5 million.
Fine. All right, next one. A coil is wrapped around an iron rod of radius 5 centimeters, a total of 100 times from top to bottom. So let me just try and help you out here a little bit. So here we go. It's a piece of iron. And you wrap some wire around it. 100 times. The flux density is 2 Tesla, so I have a magnetic field passing through it of 2 Tesla. So the first question is, what is the, and the radius here is 5 centimeters. So I want to know what is the flux linkage. So that would be N times the flux, which would be NBA, which would be 100 times 2.
That's pi 0.5
Pi or squared, 0.05 squared.
It's half pi.
The final answer?
Yeah.
So what's that as a decimal? 1.57. Webers.
Oh, the unit letters.
Yeah.
So
Some people write N Webers. I don't really like that
why n?
because there's N of them. I don't like it. I'm not sure technically if you have to. I just write Webers.
Yeah, because how can it be 0.57 on the field?
Yeah, so I don't like it. Okay, and then the next part is just what would happen if the angle is 10 degrees. So if you now shift this 10 degrees.
Times cos 10.
Yeah, that's it. So now you would get the flux linkage would equal 1.57 cos 10, and what's that, Zach?
It's a negative number.
Ah, are you in radian mode still? Yeah.
1.55, sorry. We're doing trig maths, that's why. It's our radius.
What trig stuff are you doing? Further trig?
Calculus and integration.
Ah. Okay. Is it okay? Yeah. Now, how many questions do I have in the database for this one? Hundreds, thousands? What have we got?
16.
Yeah. Nice. So you've had a couple of easy nights now, but now we're up to 16. Wonderful.
At least we got the weekend to do that.
Yeah. And I give you even better news. So we have a abundance of time in semester 2, because how many weeks to the end of the course?
10.
10. You have loads of time in semester 2. Because I told you that Connell said I can't give you more than 7 weeks to work on the coursework, and I want to make a submission date at the end of the semester.
Yeah.
So I'll have to wait 3 weeks before I can start it, and then there's
Okay.
plenty of time. So what I was thinking of doing was giving you the time in the second class this morning to get these 16 questions done.
Okay.
And then that should really ease you up for the weekend then.
Yeah. Thanks.
Because they're not that long. Well, you might find a couple of hard ones. Yeah? Unless you want to do all 16 for the weekend.
So,
Just go home now.
That would be nice, but what would be even nicer is if you did the questions now.
So that you know the saying, due tomorrow, do tomorrow.
I don't I know the sentiment, but I don't know the saying. What's wrong, Dorian?
no,
You don't want to do the questions now?
so just the double.
We have a double class,
Okay.
so